We will continue problems on chapter 3. We have first, we have already solved problem 4, so now with problem 5. A steel specimen of modulus of elasticity 30 times 10 to the power 6 lb per inch square in a compression test has a starting height of 2 inch and diameter of 1.5 inch. The metal yields with a 0.2% offset at a load of 140,000 lb. At a load of 260,000 lb, the height has been reduced to 1.6 inch. Determine first the yield strength and the flow curve parameters, the strength coefficient, and strain hardening exponent. Assume that the cross-sectional area will increase in a uniform way during the test. Okay, so first, as a first step, here we use English units. It's not a big deal. When you have English units, instead of Newton, you put lb. And instead of meter, okay, you can deal with inch or feet. So keep the units as they are. You don't have to convert anything. Keep, since they gave you the measurements lengths in inch, you keep them in inch and forces in lb. So first, we want to determine the yield strength. What is the information provided about the yield strength? We know that the metal yields based on the 0.2% offset method at a load of 140,000 lb. So we have the value of F, okay, and F yield is given. So now all we have to do to find the yield strength is to divide by the initial area, okay? So always remember yield strength and tensile strength are found based on the initial area. So to calculate the yield strength, it is the value of F, Fy, over the A0, okay, over A0. And in order for the initial area, you have the initial diameter of your specimen. So you know that the area is pi d squared over 4. So we can replace simply A0 by pi times d square, d0 of course, d0 square over 4. And in this way, you can calculate the value of the yield strength. And it's an engineering value. Now, the second question is to find the flow curve parameters. We want to find the strength coefficient, okay, and the strain hardening exponent. But what is the problem here is that we need 2 points. You know that in general, in order to find these two coefficients, we need 2 points. And you can say that the strain hardening zone will start from what? So if I do a small drawing, it will start from yield point until the maximum load, which corresponds to the tensile strength. So the yield point can be considered a point of the strain hardening zone. So to be on the safe side, in general, we choose points far from the limits. But it's fine if we don't have points far from the limits. We can take the yield. It's not wrong. And the yield point will verify also the flow curve. So I can take the yield point as first point. So I need the characteristics, but please pay attention. I need which characteristics? The true stress and true strain at yield point. Okay. In general, for the yield point, the true stress and strain will be very close to the engineering stress and strain. Why? Because in the elastic region, okay, if you do calculation in the elastic region, the values are very close to each other. Because still, the values of epsilon is relatively small, and this will give nearly very close results. So sometimes I confuse these values, and as I say, because they are very close, we can use one in the place of other. But if we want to be accurate, when we consider the strain hardening curve, we should do the calculation of the true value, the true stress at yield and the true strain. Okay. Now, so the first step to do is to find the true stress at yield point and the true strain. Already I have calculated the engineering stress at yield point. So sigma yield engineering is already calculated. So I can easily find, if you want, the corresponding value of what is the condition to be able to do so. I should find the value of epsilon, because you know that sigma through and sigma engineering are related through epsilon engineering. So I should get what is the value of epsilon engineering at the yield point. Okay, and in order to get it, I will use which given. I will use the given that the metal will yield at 0.2% of set. Okay, how I will use this information? If you remember, we said previously last time. So let me clear the figure a little bit. So let us say this is your curve. So I have first sigma axis, epsilon axis. This is on the engineering curve. And I have the variation of sigma with epsilon. So I have first nearly a linear profile. And after this, I have, here I have a transition. So, and after I have the strain hardening zone. And after I have rupture. Okay, this is the profile of my graph. Sometimes the yield point, which is the transition, is not very clear. This is why the technique we use is the 0.2 offset method. This technique consists on the following. We take, at the point, we take epsilon equals to 0.002, and I draw the line that is parallel to the linear part. So of course, what is the slope? Here you can see هون مبينين بعاد عن بعض, but in reality they are very close to each other. So this is just for you to see how we do it, but this point is very close to 0. So in this way I can detect the yield point, which will be the transition from linear to plastic, from elastic to plastic zone. So I can say that the slope here is what is the modulus of elasticity. Okay, so the slope is equal to delta sigma over delta epsilon. And what is delta epsilon? Delta epsilon will be epsilon yield at yield. So I will say epsilon yield. Epsilon yield minus 0.002 is delta epsilon. So I can write that the modulus of elasticity E is equal to delta of sigma over delta of epsilon. And then for delta sigma, sigma at the second point is sigma yield, and sigma at the first point is 0, because I'm starting from the epsilon axis, so sigma is 0. So I get sigma yield minus 0 over epsilon yield minus 0.002. Okay, this is why here, since E is given, the elasticity modulus is given, we have calculated together sigma yield. Then you can say that epsilon yield is equal to the modulus of elasticity is equal to sigma over sigma y over the modulus of elasticity, and we should not forget to add 0.002. So this is why here we add 0.002, because delta epsilon is epsilon yield minus 0.00. Okay, so in this way yes.
وقتها إذا سألتنا بالفحص إنه بدك the yield strain بيكون بدك epsilon y مش delta epsilon، ما هيك؟
مظبوط.
Okay, thank
you. So I ask you for the yield strain يعني بدي epsilon y، يعني أنتم بتجيبوا الدلتا and then you add to it delta epsilon هي sigma y over E. You add to it 0.002 to get epsilon y. Okay. because epsilon yield is counted from 0. مظبوط? It's counted from here, while delta epsilon is counted from here. This is why to obtain the total epsilon value, I should add this part, which is 0.002. Okay? So, now, in the next step, okay, since now I know the characteristics of yield point, and these are the engineering characteristics, I can use the formulas I know to convert. And because I know the relation between a true engineering, a true stress strain value and engineering stress strain value, I can relate them through the formulas we have developed last time. If you remember, we have demonstrated together the relation between epsilon engineering and epsilon true, and the relation between sigma true and sigma engineering. So we can convert easily from one to the other. But you will see that for the yield point, the values will be very close, and they will start to differ in the strain hardening zone. Okay, now I need a second point. So if I continue reading, they said that at a load of 260,000 lb, the height has been reduced to 1.6 inch. Okay, so these characteristics will give me the second point. What do I know? First, I know the force and I know the reduction in height. And it's very important to use which concept I have. As I said, assume that the cross-sectional area is increasing in a uniform way. This information will help me to find what? What they gave me the reduction in height. What I am interested in is not the new height. I want to know the new cross section. Okay, how to find the new cross sectional area? Which concept I should use? Yalla, tell me how you solve this problem. What should you do? You have the concept of conservation of volume, okay? So don't forget it. Always, when they say conservation of volume is always here, but before necking, I have, if you want, in general, in tensile tests, I have elongation over the whole specimen. So I can say that cross-sectional area is the same everywhere. After necking, this relation will not apply. In compression, what will happen in general is that we have, due to compression, we have a small deformation. Yani it will be, if you want, like this. It will do this shape, because at the ends it will tend to, you are compressing between two plates. You have here at the plate contact, you have opposition to expansion. So this will lead to, if you want, the formation of a higher cross-sectional area in the middle zone. But we will neglect this effect here, since they said assume that the cross-sectional area is increasing uniformly during the test over the whole specimen. So we can apply, due to conservation of volume, we can write that A0 times L0 is equal to A times F. So we can say that the ratio of areas, so A over A0, is equal to L0 over L. And here we have the ratio of the height, because L0 is 2 and the new height is 1.6. So now we can deduce the value of the new area A. Okay, we can deduce from here. So A is equal to 2 times the initial area, which is pi d squared over 4, pi d0 squared over 4. So 2 times pi d0 square over 4 divided by 1.6. Okay, so from here we can get the value of A, the new value of A, and then we can deduce the value of true stress, okay, at this point. So the true stress at this point will be, once I find this area, all I have to do is to divide the force. So I have the force at this point is 260,000 lb. I divide by the corresponding area, and then the next step to do is to find the strength coefficient and the strain hardening exponent. Okay. Once I find, of course, I found the true stress at this point. I still need to find the true strain. To find the true strain, I apply the formula that epsilon true is, so epsilon true is equal to ln of, of course, in compression, okay, you will have a negative result because you have that what is happening, the length is decreasing, okay, so you can just put a minus and you get the value of epsilon. But we can when you want to find the strength coefficient and strain hardening exponent, since both are negative, sigma negative and epsilon negative, okay, then you can consider the absolute value and find k and n, because once you say that it's in compression, then you know that these values are negative. Okay, so if you want, let us see the calculation a little bit to see them in numbers here.
Best doctor, I have a question.
Yes.
Can't we use the height اللي هي 1.6 كمان نلاقي الانجينيرينج سترين وفينا نلاقي الانجينيرينج كمان ستريس، فبعدين نلاقي الفورمولاز تنلاقي الترو سترين وترو ستريس.
You can, بس انه why not directly applying because
يعني اذا ما فكرنا بالconservation of volume يعني.
ما اذا ما اجباري، اذا ما عملت الconservation of volume how you will okay, yes you can, yes of course. قصدك تملئ الاريا بلاقي الانجينيرينج strain and I find the engineering, yes you can, of course, it is equivalent, you can do it. But this method will be, it's faster for you if you paid attention to this.
Okay.
So as you can see, as we did first in the first question, we found the value of A0 and we divided the force by A0 to get the yield strength, and of course it's an engineering value, and to get the epsilon, the corresponding epsilon, we did first delta epsilon. هلا here the solution ما كتير accurate بالاسامي، هيدي delta epsilon لازم تكون. This is delta epsilon. This is why, for you to understand why we added 0.02. Okay, so this is why take note. النوتس بفسروا لكم شو عملوا. This is delta epsilon, and then here we add 0.002 to get the strain. Okay, now if you want to, if they ask you هون it is an additional، هون مثل ما قلنا بدهم يجيبوا true strain with true stress values. Okay, وحنشوف انه they will be very close. Here what they did is that they found the new to find the new height at strain. now we have the initial height. Okay, we can use epsilon لانه epsilon is by definition, epsilon engineering is equal to h minus h0. okay, over. هلا انتبهوا على شغله، اذا انتم حاطينها positive الابسلون، اذا عم تاخذوا absolute value بدكم تعملوا h0 minus h. اوكي، لانه نحن عاده epsilon engineering we define it as h minus h0 over h0، بس بالcompression بتكون negative value. اوكي، so if you take the absolute value، اذا هون اخذوا هن عم بيعملوا calculation ل absolute value in compression، كانه كتبوا epsilon engineering compression، ساعتها بتصير definition h0 minus h over h0. okay, لأنه شلنا الماينس so we should take the opposite value, and since we calculated epsilon engineering and we know the initial height, then we can deduce the corresponding height at yield. okay, هذا اللي هن عملوه. they calculated the height at yield. This will allow them to calculate the true strain. Okay, لأنه the true strain هو ln h over h0 إذا عم ناخد the negative value. إذا بدنا ناخد the absolute value هو ln h0 over h. So and based on h, they calculated the value of the area due to conservation of volume. And from here, they calculated the true strain by doing the force over the actual area. هلا مثل ما قالت رفقتكم, if you don't want to go to find the corresponding area, you can directly apply relations between true stress engineering stress. Okay, ويعني هول الريليشنز اللي شفناهم last time here. So these are the relations that you can directly apply. You have that epsilon true هي ln 1 plus epsilon engineering. And once you find epsilon engineering, you can calculate epsilon true. And you have that sigma true is sigma engineering times 1 plus epsilon. يعني بمجرد ما نلاقي epsilon engineering و sigma engineering, no need to calculate the areas, the actual area. We can go back to this relation to get the true values. And this is a second method. Okay. So now, if you compare values, مثل ما قلت لكم at yield, they will be very close. And if you look at the value of sigma engineering at yield was nearly 79,224, while the true value is 78,000. It's very close. Nearly, the difference is maybe less than 1%. If you do the comparison. If you do the relative error, it's not a very high. This is why in the elastic region, sometimes they say, the true and the engineering values are very close, and we can consider them the same. But to be more accurate, I advise, and you should do this. This will show that you understand that the flow curve is based on true values, not on engineering values. Okay. Now, also, we did the same procedure now for a force of for the second point. So for the second point, as we did together, they found the actual area, okay, and they divided by the actual area to get the true stress. And for the true strain, they used ln h0 over h to get the true strain in absolute value. So now you have the true stress and true strain for 2 points, the yield point and the second point. So now what you can do is you can apply 2 equations with 2 unknowns. Okay, if you can see that they considered the same value of epsilon, because epsilon will be very close and you can verify it. Okay, you can verify if you do ln h over h0, you still get a very close value to the engineering value. This is why they used it here. So for the first point, they considered the values of yield, and for the second point, they considered the values for f equal to 260,000. So now you have a system. Okay, all you have to do is to say that the flow curve should satisfy the equation sigma, of course, true values, okay, of sigma equals to k, which is the strength coefficient, times epsilon true to the power n, which is the strain hardening exponent. So now I will apply for both points. They should verify this rule. And in general, always first we find n by dividing the 2 equations. Okay. So if you divide sigma 1 over sigma 2, k will be simplified. K is in both terms, and you will get then epsilon 1 over epsilon 2 to the power n. To find n, what you can do, so this is your equation. You do ln from the 2 sides. When you do ln from the 2 sides, n will be, and you have ln 1.493 equals to n times ln 48.06. So you can get the value of n. And once you find n, in order to get k, all you have to do is to take now one of the 2 points, and you apply sigma equal k epsilon n to one of the 2 points, you get the value of k. And from here, you can deduce the equation of your flow curve. Okay? Any question on this?
Clear, doctor.
Okay. So let us start with another problem. The Brinell hardness problem, we have done it together last time. So just as a reminder, all you have to do here is to apply an equation, but just pay attention for units. Yeah, in this equation, the force F is in kilogram. You know that the force in general is in Newton. But why we can give the value as kilogram? Because in general, here what we mean by the force, it's equivalent to the weight of the ball we are using. Okay, and the weight is proportional to the mass. It's m times g. Okay, so this is why sometimes I express the force by m. So if in case they gave me the weight, all I have to do is to divide by g to get m, corresponding value of m, and then do not forget to replace f in kilogram. If you replace f by the weight value, you will get a wrong result. And for the diameters are replaced in millimeter, not in meter or centimeter. So just here, the main issue in this formula is to respect the units. If you respect the units, it becomes just a numerical application. Okay. Problem 7. This is the last problem in chapter 3 problems. A 125 millimeter diameter shaft rotates inside a fixed bushing whose inside diameter is 125.6 millimeter and length is 50 millimeter. The clearance between the shaft and the bushing is a lubricating oil whose viscosity is 0.14 Pascal seconds. The shaft rotates at a velocity of 400 revolutions per minute. This speed and the action of the oil are sufficient to keep the shaft centered inside the bushing. Determine the magnitude of the torque due to viscosity that acts to resist the rotation of the shaft. So here maybe it might be a little complex when you read it, but when you do a figure, you will see that it's simple. So what we have here, we have a shaft, okay? And we have a fixed bushing around. So they gave us the information about dimensions. So here I have a diameter of 125 millimeters, and I have that the outer diameter is 125.6. Okay, so I can deduce the clearance. What will be the clearance between them? By simple calculation, it is 0.3 millimeter. Okay, because what you will do, you will subtract 125.6 minus 125 over 2. Why over 2? Because I have the clearance from both sides, here and here. So the clearance here between the two will be equal to 0.3 millimeter in dimension. So this is 0.3 millimeter. Okay. Now, the next step is what I have is that the inner shaft is rotating, and they gave me the velocity of rotation. So it's rotating at 400 revolutions per minute. Okay. So here I have W is given for the inner shaft, while for the outer shaft they said it's fixed. So W for the outer one is 0. No motion for the outer system. Okay. Only I have rotation of the inner shaft. And for the inner shaft, W is equal to 400 revolution per minute. Let us convert to the SI unit, which is radian per second. So this will correspond to 400 times. Each revolution is 360 degrees, which correspond to 2 pi radian. So I multiply by 2 pi, and 1 minute is 60 seconds. So I divide by 60. This will give me the result. When I do times 2 pi over 60, I get the speed, I get, if you want, omega in radians per second. Okay? And then What I am interested in is linear velocity. Why? Because you know that in general, when we talk about viscosity, okay, viscosity is related to variation in linear velocity. And to find linear velocity, when you have rotation, what is the linear velocity? It is omega times the radius r. So here I have that the radius of rotation is 125/2. So to get the linear velocity, I will have v equal to omega times r. Okay, so equals to omega times 125/2. And if you keep the dimension in millimeter, your velocity, your resulting velocity will be in millimeter per second. So if you do the calculation, you will get that the linear velocity is 2,618 millimeter per second. You can also convert it back to meter. It's 2.618 meters per second. Okay, so in this way, we have calculated the value of the linear velocity. Now, next step is to calculate. We want to relate to what we know. Okay, we have seen together that by definition, the shear rate tau, is related to the gradient of velocity through what? Through the viscosity. So it's the viscosity times the shear rate, gamma, if you want, you can call it. So it's equal to mu times del V by del Y. What we mean by del V by del Y is the gradient of velocity. Here, how to calculate the gradient of velocity? I know the linear velocity at this point. I have calculated it. It is 2.618 meter per second. I know that on the outer shaft or on the outer side, I have a velocity of 0. So to calculate the gradient, it's v minus 0 over the distance between, which is the clearance. Okay. So in order to calculate the shear rate, all I have to do is to divide the value of the linear velocity, because it's v minus 0, so delta v. So here I can write, assuming if you want a linear profile, whenever you have a very small clearance, you can assume that you can assume due to the small distance, and no, I can take it as linear profile. Or also when we have constant viscosity, in case of a fluid with constant viscosity, the variation of velocity will be linear. Okay, so here I can consider that the shear rate tau can be calculated as mu times delta v over delta y, and delta y represents the clearance. So this is the clearance, and delta v will be v minus 0. So tau is equal to mu, which is given, times v minus 0, okay, over the clearance, which is 0.3. Okay, why I am calculating the shear? Why? Because they asked for what? What was the question? Determine the magnitude of the torque due to viscosity that acts to resist the rotation of the shaft. So whenever you need to find a torque, if you want to calculate a torque, you need a force. This is force times distance. Okay, what will be the torque? It will be the force of resistance to rotation, because look, when the inner shaft is trying to rotate, oil will develop a shear rate that will oppose rotation. Okay, and this shear rate is calculated through mu del v by del y. And once I find the shear rate, okay, which is the shear stress, I mean. Once I find the shear stress tau, Okay, I can find the total force because shear is what is force per unit area. Okay, so if I want to find the force developed, all I have to do is to multiply by the area. Okay, so whenever I get the value of my shear rate, which is in Newton per millimeter square, I can then multiply by the area of my shaft, okay, and in this way I can get the value of the force developed, and then to get the torque I multiply the force by the radius. Okay, so this is the strategy to do. Here what I will do here, so first I will calculate. So in steps, if we go back to steps, the first step is to find the linear velocity. Once I find the linear velocity, I divide delta V by clearance. Yani it's V minus 0 over D. I get the shear rate. Once I get the shear rate, I calculate the shear stress. So this is the shear stress. The shear stress value will be in Newton per millimeter square. Okay, and after this I will divide by the peripheral area of the shaft. يعني انتو the shear rate, okay, is acting on the external on the peripheral area of your shaft. What is your peripheral area if you want to calculate it? Okay, so here you have that the total length is given. Okay, you have that I have a length of 50 millimeters. So this is my shaft. The length is 50 millimeters. And I have the diameter my diameter is given. It's equal to 125. Okay. So what will be the area exposed to shear?
The outside area of the cylinder.
Yes, it's equal to what?
2 pi
no,
r times 50.
Yes, exactly. So I should do the 2 pi r, which will give me the perimeter here, or if you want, pi times d, okay? And I multiply by the length. I get the peripheral area that will be subjected to the shear, and then I multiply this area by the shear stress, okay? I find then the value of the force, and once I have the force, the total force acting, to find the torque, I multiply by the radius. Okay, so once I find the shear stress, I multiply by the peripheral area, and once I do this step, to find the torque, I multiply the force by the radius, which is 125 over 2. Then I get the value of my torque, and in case I kept the dimension in millimeter, I get the torque in Newton millimeter. And in case I can convert back to meter, I divide by 1000, I get 1.506 Newton meter. Okay?
Doctor, there's less than 1 minute left, but can you send us another exercise مثل هيدا تبقى؟
Okay. Yes, I will.
Thank you, doctor.
Any other question on this?